we're going to try to understand spring forces using data first and then math later. The first tool we need for this is what we call a motion sensor. So inside of this cart that you see me moving around here, there is a kind of internal gyroscope, some kind of sensor that allows it to track its horizontal position at different moments in time. And you can see it being graphed there in real time. The cart right now, the way it's calibrated, is perceiving leftward motion as positive and rightward motion as negative. But of course, we could change this later if we wanted to. So that is essentially all there is to a motion sensor here. We also need force sensors. A force sensor is just some other device. Sometimes it has a hook, but essentially by pushing on it, it reads how many newtons you're pushing with and or how many newtons you pull with. So this force sensor is set up in a way that perceives pushing motions as positive and pulling motions as negative. But of course, that could be calibrated the other way around too. So what we're going to do is we're going to connect these two together, the cart and the force sensor, along with a spring. And on the computer, I'm going to graph force calculated on the vertical axis and position on the horizontal, and we're going to see what relationship these two things have. The force of the spring versus the position of the cart, which corresponds to how much the spring has stretched. So hopefully you can make out on the computer there, those little blue dots being graphed are different forces that the sensor is reading for different positions of the cart that it's attached to, right? So essentially what this is showing us is approximately a linear relationship between the force applied by the spring and how much it is being stretched. And this is what is known as Hooke's law. Okay, so you just saw some data that I gathered using a force sensor and a motion sensor to sort of gather some data about how the spring force relates to position. But before we get into this, I want to go over a really important idea about the relationship between mathematics and science that isn't stressed enough. Because these are two branches of knowledge that kind of think very differently. So scientific reasoning, which is essentially what this class is kind of all about, right? Unfortunately, kind of gets a bad rap when it comes to high school because you guys don't practice it enough, right? You guys mainly, for most of your science or math classes, you've probably done this, or we call it deductive reasoning. So essentially, deductive reasoning says we start here. We start with the equations and the variables and the relationships, but they're all abstract. And so you get an equation, you manipulate it enough, and then maybe eventually you get to the data and you try to plug in data later. But you spend a lot of time in your math classes just focusing on this, and then maybe you get over here, which is why word problems are so difficult. Because you don't practice them enough. Whereas the scientific reasoning says, okay, we're not going to start with the abstract stuff over here. No, we don't want to start there. We want to start with what are the actual facts on the ground that we can observe right now. We start with the data. This is what we start. What do we actually see in front of us? And then, only then, we say, okay, how can I figure out a mathematical relationship that makes sense of the data in front of me, right? So this is a sort of different way of thinking that essentially this class stresses a lot. And we haven't really talked about that as much. I mean, it should be talked about in every single science and math class. And yet I find in my experience, this subtle distinction is not brought up very often at all. Again, this is why you guys do not enjoy word problems, is because you're almost never doing this scientific reasoning. You always start here in most high school math or science classes. So that's a huge problem, right? That's maybe why AP Physics is a struggle for some people. It's bad inductive reasoning. So we're going to start with the data, right? This is all we have. Forget the equations and everything. We'll worry about that later. So let's just make sense of what we're actually looking at here. So keep in mind, right, when it says position, this is actually the position of the cart. Right, so let's just, what does all this mean? So we have a spring. It was attached to a force sensor, which was on top of a cart. Right, and essentially what I was doing is I was sort of pulling it to the right, and what would happen is the spring would stretch, right, some distance. Here's the force sensor in the cart again, right? And the force sensor would read some amount of sort of pulling force from the spring. We could call this force of the spring. I'll just use S for spring. Whereas, at the very beginning, Fs was equal to 0, right? And so this is a graph where it tells me where the cart was, and it tells me what did the sensor actually read. And it turns out it's a linear graph, right? And so I gathered this data in my Pasco data collection software. I was able to run a linear regression. And so now, again, scientific thinking, we've got to think about, okay, what does the slope tell me? Right, so maybe first off, we see that the slope is 3.51, but what are the units? Right, we can actually figure this out. Well, the units are, looks like newtons on the y-axis, meters on the x, and so if the slope is like a rise over run calculation, we have a change in force divided by a change in position, right? So the units here seem to be newtons per meter, right? The newtons of force over the units of distance. So what does this actually mean, right? It's basically telling you, for every increase of 1 meter, there is another increase of 3.51 newtons of force. It's essentially what it's saying, right? If I go over here, if this equals 1, this equals 3.51. And that slope is constant all throughout, right? And so essentially what we can say is change in force over change in distance, right? See how we started with the data and now we're getting to the mathematical model is equal to, we're saying 3.51. And so now I can actually start to get some sort of relationship here. Now, let's keep in mind the y-intercept before we sort of make a little bit more sense of this thing over here. So our y-intercept is a very small number here. It looks like it's very close to 0, but not quite. Even if you consider this uncertainty here, it actually isn't, the window does not contain the number 0. And there could be reasons for why that is, right? So if you think back to the video and you're very careful about exactly how the setup looked like, well, it kind of looked like the spring was sort of sagging a little bit when it was connected to the cart here. And so maybe there actually is like some very slight spring forces being applied to the ends of the spring. The spring is always going to exert force at the endpoints, kind of like a rope. So it's kind of like tension, except the tension force in this case can change depending on how stretched out the spring is. And so, maybe that slight bend in the spring created a non-zero force at the endpoints, right? And so that's why this intercept, this y-intercept, when the cart is at a position of 0, right? Because it's talking about this point over here, right? It's at a position of 0. It actually is not, it's like slightly underneath, right? The y-intercept is at negative, 0.0314. So anyway, that's kind of interesting, right? So just goes to show you, right? This spring is not ideal or maybe not perfect, right? There's experimental error, etc., right? There's all sorts of factors on a y. It's not doing exactly what we expect, but what we can say is, if we had an ideal spring, then it should have a spring force of 0 when not stretched. Right? Intuitively, that should make some sense. If you haven't stretched it at all, there's no reason the spring is going to try to pull back to its original state or sort of push out. So for an ideal spring, we could expect that to be 0, right? So the idea is if we keep going with this relationship, this slope should be true for the spring force at some distance x, and also the spring force, let me put a little x here, at distance 0. Right, so we could say at position x minus position 0, this should also equal 3.51. But of course, for an ideal spring, this guy is 0. Right, so that goes away. Now, I've written this a little weird here. We're going to get rid of the x's in a second. The idea is that the spring force is equal to some number, right? So for our particular spring, we had this 3.51. We call this the spring constant. And you can imagine that different springs are going to apply different amounts of force for the same amount of stretch, right? So the spring constant changes for each spring. And so sometimes you're given that information, sometimes you have to solve for it, right? But that the spring force is equal to whatever its spring constant is times x. Now there's one sort of caveat, or maybe two caveats we need to make here. So number one is this equation also works. You know, we've been basically looking at these as magnitudes, right? So this is true for magnitudes. But it is also similarly true if we think of this with direction as well, except, again, there's a slight caveat here. So if we make these vectors, in fact, what I should do is actually, it will make a little bit more sense if I treat this as a displacement vector instead of position. Let's think about what actually happens in different scenarios here, what these vectors look like. So let's imagine these three scenarios. Here's another one. Let's also imagine when the spring is like pressed down. We call this like compression. So I have a cart here. So just a few terms to get out of the way. When the cart is at, we called this position 0 or x equals 0. The spring actually has some length to it already. So we call that the equilibrium length. The idea is the spring will always try to establish equilibrium where it's exerting 0 force on either end, right, to whatever objects it's attached to. If it's longer than the equilibrium length, it's going to try to pull itself in, pull itself shorter. If it's being compressed, it's going to try to push itself out, try to make itself longer. So sometimes we abbreviate this as LEQ, right, in physics. But the idea is if we have stretched beyond LEQ or we have compressed so that we are shorter than LEQ, we're going to exert a force. And the force is going to actually have different directions. So like in the compression case, the force the spring exerts is outward. This is the force vector from the spring. Whereas in the stretching case, we already saw it's going to pull itself inwards, right? And let's think about the displacement vectors, right? So what would the displacement vector be if I already said my 0 point is here? It would be a vector that starts here and then ends where the new endpoint of the spring would be. So that's like this. That's our displacement vector, right? They're going in opposite directions. Same thing over here, right? If my 0 point is here, then my displacement vector would start here go all the way out here. And this would be my displacement vector. Again, going in opposite directions. So the idea is, if we're going to look at this as a relationship between vectors, we have to have a negative right here. So that right there, my friends, is a very good model for spring forces. And we can apply this to real world springs. There's always going to be some like error, some deviation for actual springs. No spring is perfect. So this is only meant to be for ideal springs. And most springs are pretty darn close to ideal, but some springs are all messed up, right? I mean, you probably owned a Slinky at some point. Like there was probably a point at which your Slinky looked like this. It's not going to be working like an ideal spring like it used to, right? So ideal springs are like perfectly coiled. You know, they're not bent anywhere, and they're going to perfectly, you know, apply these forces. We also say that springs exert a kind of force that we call like a restorative force. Right? It's trying to restore equilibrium. Right? So that's the idea where, you know, if it's stretched out, it's going to sort of pull itself inward. If it's super compressed, it's going to sort of push itself outward until it reaches, you know, its nice equilibrium length. You know, if this is LEQ. Right? So in different problems, you're just going to be calculating the force of the spring in various ways. Sometimes you're given the force of the spring, sometimes you're given the spring constant, sometimes you're given how much it's stretched, right? It can always change, but most of it relies on this equation here. But it's always good to know where that equation comes from. It comes from the data, actual real-world data that you can gather about springs, right? And so we gathered that data. So now you should really understand why the equation looks the way it does, and we can sort of dive into some problems. Okay, so let's say we've got this situation. We are at rest, or the mass is, and we have this man pushing up with 20 newtons on the mass. The mass is hanging by a spring from the ceiling, and the spring has stretched a little bit, which, you know, we might want to go ahead and, you know, we could call this delta x, right? And the question is, how far has the spring stretched? So we want to find this thing, right? So it's not going to be this entire length. We just want this stretch length, right? So depending on the problem, they might ask you how long the spring is, or they might ask you for the stretch length. So you just got to be careful about what you're looking for here. Okay. So where do we even begin? Always begin with the same thing, right? Newton's second law. Acceleration equals sum of the forces divided by mass of the system, right? So we're going to do the mass of the block. We know that the acceleration is 0. Why? Because we're at rest. Now, what are all the forces on the block? And let's be very careful here, right? A lot of you guys like to skip this step of drawing the diagram. You just want to jump straight into plugging in numbers. It's a little bit more complicated than you probably think, right? What are all the forces acting on the block? There is obviously force of gravity, which we know is, 1,000 newtons? There's obviously the man pushing up. This seems like a pretty small force here, 20 newtons. This is definitely not drawn to scale, that's for sure. This force of gravity vector should be much, much longer. There we go. And we also we actually have a third force, right? So there's the force of the spring. And we can already tell, right, this force of the spring is going to be much bigger to sort of compensate for the force that he's pushing up with. So we can call that Fs. And so now we can actually start putting some stuff in, right? And we have labels for all these, right? We have two forces going up. So in this sum, we're going to have Fs plus 20, and then minus the force of gravity, so 1,000. And that's divided by the mass of the block, which is 100. Well, if I multiply both sides by 100, I get 0 equals force of the spring minus 980 newtons. So the force of the spring is 980. And they also want to know how far the spring has stretched. Now, I think we wrote this problem a little too quickly. I did not tell you what the spring constant is, so let me go ahead and give you that information. That would be good to know, right? Let's say our spring constant is, let's make it a little higher. Let's say, let's say 20, sure. 20 newtons per centimeter. Let's throw a little twist in there. Interesting. So not meters, right? So if I go over here, I get 980 newtons is equal to 20 newtons per centimeter, right? This is my K value. And then times how much I stretched by, right? So if you solve for delta x, you get 980 newtons divided by 20 newtons per centimeter. And check it out. Newtons cancel with newtons. We're left with centimeters, not meters. Units matter. And this is going to be 49 centimeters. That right there would be the stretch length, right? It's a nice little problem to start with. So if you're ever lost and you know forces are at play, I guarantee you, just writing this out is like 20% of the work. It will help you get the problem started. You won't even have to think about it. Just write it out and then start thinking, okay, what forces go here? What is the mass I'm looking at? Is this 0? Is it not 0? Is it given? Right? It's always a good starting place, Newton's second law. There's also other problems that are a little bit more creative, where you don't have any numbers at all. And this is actually a former AP problem that I actually really like. So if the above mass is at rest, find the amount the spring was stretched, right? Why are we able to say this? Do we know that the spring was stretched at all? Is it possible for this spring to sort of already be at its equilibrium length? Well, no, right? Because that would imply that, the spring force is equal to 0, even though, we know there's a normal force like this, right? There's also the force of gravity. But if the spring force was 0, the block should have some net acceleration going this way, right? It's not moving. So what's happening here is that we have sort of, maybe someone attached the mass to the spring at some point in time and just gently let it slide down so that maybe the equilibrium length is just a little bit smaller, and then it stretched some other distance past that. So we do have a spring force, right, sort of pulling this way. So we don't have any numbers here. Spring constant, we're just going to call K. This is the stretch length. We have some general angle here, and we don't know what the mass is, right? We're just going to work with the letters, though. So good place to start, free body diagram, always. All right, so put a dot there. We've got force of gravity going down. We've got a normal force, which is perpendicular to the surface. And then, of course, we have a spring force. And keep in mind, right, if we were truly trying to be accurate to this situation, we would have to make sure, right, that this component of the force of gravity is the same length as this one, and that this component of the force of gravity is the same length as this one, right? We have a balanced force diagram here. The net force should equal 0, right? So all these force vectors should cancel out. But anyway, so this is our free body diagram. So if this is true, then we know, in fact, I actually shouldn't have erased these components, right? We could call this one, typically on ramps, right? Remember, we like to angle our axes to sort of solve for these components here. So like we could call this one FGX. We could call this one FGY, right? And so we know that these two vectors are balanced, and we know that these two are balanced, right? But we actually only need to sort of look at the x components here. So now that we know that, we can start with Newton's second law. Again, that's always a good starting place. So the acceleration should equal the sum of the forces. We're looking at the x acceleration and the x component of the net force here, divided by the mass. Well, we know the acceleration is 0. And we also know if this is the positive x direction, right, going down the ramp, then we would say that the force of gravity in the x direction is positive, whereas the spring force is acting in the negative direction. So we would say in the sum, we would have Fgx minus the force of the spring divided by the mass. Well, the only way this could be 0 is if these two, the numerator is equal to 0, right? Just multiply by m on both sides. And the force of gravity in the x direction, well, we can find that, right? So draw the triangle. So we have a triangle here. What is this angle? What is that angle? Well, this angle is the same as this one, which I think, just double check here, I think this should be equal to theta. Right, this angle, and by the alternate interior angle theorem, this angle is equal to theta. I mean, you could think of this triangle as well. Maybe that's a little easier, right? So in this case, sine of theta equals, right, these two sides are congruent. So this should equal Fgx divided by Fg. And Fg is just m times g. So the x component of the force of gravity is m times g times sine of theta. Cool. So I go back over here. M times g times sine of theta minus, it's going to be the spring constant times the stretch length. That should be equal to 0. So that means that k times the stretch length equals m times g times sine of theta. And that means that the amount we stretch by is m times g sine of theta divided by k. And again, I think we mentioned this in a previous video. What we have here is what typically they call in the AP sort of grading, score sheets. If you ever look at FRQs and how they're scored, they actually give points. Usually, if you sort of point out a kind of functional dependence in a lot of cases. So we call this functional dependence. When we don't really have any numbers involved, we just have an equation that relates certain variables to each other. And typically, what they do is they have you sort of think about, okay, if theta increased, what would happen with delta x, right? If k increased, what would happen with delta x, right? Because delta x depends on this thing and this thing, right? So consider these because they could easily ask a follow-up question about this stuff. So what would happen with delta x? Well, if theta increases, then mg sine of theta over k also increases. And therefore, delta x increases. So this is a very a mathematical approach. But also we could take a very scientific approach, right? So essentially, if you imagine making this ramp a lot steeper, intuitively we kind of know it's sort of like we are increasing the force of gravity along the x direction acting on the mass here, right? If I draw my force of gravity vector straight down, the x component going down the ramp is a lot larger, right? So essentially because the force of gravity down the ramp is getting larger, the spring force has to sort of compensate in order to establish an equilibrium, right, for the mass to be at rest. And so the spring force also has to get bigger. How does it get bigger? By increasing the stretch length, right? So that should kind of make some intuitive sense too. What would happen if k increased? Well, if k increases, then mg sine of theta over k decreases because you're increasing your denominator. So the value of the thing, the fraction, gets smaller. And so we can say that the stretch length should be smaller. And again, that makes a lot of intuitive sense too. So think about this. If k is very large, then that means it doesn't need to stretch as much to apply the same force. Right? If I have a spring constant equal to 2 newtons per meter, and then I have this other spring that's equal to 100 newtons per meter. If I want to apply 100 newtons, right, this spring would have to stretch 50 meters, right? This spring would only need to stretch 1 meter. So another way to think of the spring constant, K, is kind of like stiffness. It's like the stiffness of the spring. The stiffer it is, the less you have to stretch it for it to apply a massive amount of force. Right? Whereas if it's very loose, then you need to stretch it a lot to apply a certain amount of force. Right? And so it makes sense. If K is very large, we can kind of think of it like the spring is a lot stiffer. And you don't want to actually write that on an AP. I don't know if they'd actually give points for that kind of thinking necessarily. They actually prefer you to point out what happens in the functional dependence, but you could argue like this. K represents the stiffness of the spring. The spring is stiffer, and therefore this stretch length, or the amount it stretches, should be a lot smaller, right? So all of these quantities represent like physical realities, is my point. And so you want to be versed in the mathematics for sure, but you guys have a habit of over-relying on your mathematical abilities. And you have no idea what these things correspond to in the actual real world, and you get lost in some of the more creative problems, right? So make sure you understand the math and the physical reality behind the variables you're using. And with that, I think I am done. So I'll go ahead and post all this stuff in the drive for you guys to look at later. And you should have some spring force problems sort of available to work on now.